All right, now for the redo of spring potential energy. If I go quiet, it's because I forgot what I said when I made this video like 2 weeks ago. All right, so spring energy, specifically spring potential energy. So spring energy is the potential energy stored in an elastic device. So like I said before, that can be a spring, it can be a rubber band, it can be anything that stretches or compresses. If we want to turn our spring potential energy US into KE, then our system needs to be the spring and object system. And I just realized that I had this going very fast. All right. So our system needs to be the spring, because our spring is where we're storing our US. And then our object, because that's what has KE. Right? So if we want spring potential energy US, we need a spring. Now, if we want to turn our US into KE or UG, remember with UG, we need to have the Earth, an object in our system, because the Earth creates the gravitational field, and the object is in that field. Our system would need to be the spring Earth object system. So we'll have to pay attention to that. And when we get into work, we'll talk about how defining our system can kind of change how we analyze the problem. So remember, UG needs Earth and object. If we have US in our system, then our spring needs to be in our system. Okay, so let's move on to trying to figure out how we can get the spring potential energy equation. Okay, so I'm going to go to the simulation that has both, and I've also might sneeze. Just kidding. So here we have a simulation of a block that's going to oscillate or just move back and forth on a frictionless surface. And we have a really awesome pie chart that's going to show us the breakdown of spring potential and kinetic, and then also an energy graph that'll show us a breakdown of spring potential and kinetic. And then down on the bottom right, I have my position, velocity, acceleration, kinetic energy, and spring potential energies. So we're going to use this to try and figure out the relationship between stretch length and velocity. So if we look at our energy graph, I'm going to have maximum potential at these maximum values, which makes sense because that's where my spring is stretched or compressed enough. And then I'm going to have maximum kinetic, it looks like right at the center here. So when the spring is not stretched or compressed at all. And we can kind of see that the spring kinetic and potentials kind of oscillate back and forth, right? We go from all potential to all kinetic, but our total energy doesn't change, right? That's because our total energy is conserved, right? So this is for an initial stretch length of 5 meters with a mass of 10 and a spring constant of 80. So I can pause the simulation and kind of run it forward till my block hits right at x equals 0, right? There's my position. And then I can take down the velocity. So my maximum velocity at 5 was 14 point something. Now we want to see if there's a direct relationship. So what I'm going to do is cut my spring stretch in half, and then maybe the velocity at that center location will also half, and that would mean that there is a direct relationship between spring stretch or maximum spring stretch and velocity, which might tell me that there's a direct relationship between spring potential and kinetic energy. Okay, so notice how the amount of energy has decreased. That makes sense. I'm stretching it less. Okay, so my bar graph kind of just oscillates between some lower points. Right, now I'm going to go ahead and move forward until I get to a position of 0 exactly. Ooh, and look, my velocity is about 7.07, which is exactly half of 2.5. Okay, so far I'm definitely seeing a direct relationship between velocity and spring stretch. So I'm going to do one more half. See if I can, if I do a spring stretch of 1.25, will my velocity be about 3? Okay, so I can pause it. Really, really small energy graph because I didn't stretch my spring much, which kind of makes sense. So I get to the center and I have a velocity of 3.5. So we're again seeing that halving the spring spring stretch leads to half the velocity. And again, our whole goal here is to try and figure out, what does my spring potential energy equation even look like? So I took some data before I made this video, right? I have changes in length. They're not in order, but that's fine. This graphs it for me. And the speed at that 0 position where I have that maximum KE. So this definitely looks like a direct relationship, which correlates to what I was seeing when I was doing the kind of like live demonstration. Okay. Now again, whole goal is to figure out, what does my spring potential energy look like? So I know right now that speed is directly related to maximum stretch. But in my kinetic energy equation, I have that 1/2 mv squared. So I might need to figure out, what does a v squared versus x squared graph look like? Because my spring potential energy is likely related to x squared, since my kinetic energy is related to v squared, and there's a direct relationship between v and x. If I square both sides, that relationship holds true. So what I'm going to do to kind of help me figure that out is I'm going to graph v squared versus x squared. So I know my kinetic energy equation is 1/2 mv squared, and I know the maximum kinetic is going to convert to maximum spring potential. So I need to figure out what goes in front of that x squared that I've seen, as I know v squared and x squared are directly related. So like I said, I'm going to graph v squared versus x squared, because the slope of that graph should help me figure out what is exactly in the middle there. So I went ahead and created that graph. I just asked the program to square both the x and the y data, and it gave me a line graph with a slope of 7.996. So now I'm going to see if any of the constants in my problem, or any combination of the constants in my problem, give me approximately 8. So I had a K of 80 and a mass of 10. And again, my whole goal is to combine them to give me maybe something around 8. So it looks like if I was to divide the the spring constant by the mass, that would give me about 8. Okay. So what that tells me is that when I graph v squared versus x squared, my slope is the spring potential, which remember is the stiffness, over the mass of the block. Okay. So again, my whole goal is to have kinetic energy on one side, spring potential on the other. So to multiply both sides by mass, and the only thing that's missing from that equation is 1/2. So I'm going to throw 1/2 in there. Now, what that means is in order for both of these sides to be equal, there also needs to be a 1/2 in front of the kx squared. Now 1/2 ends up canceling, which makes sense as to why it doesn't show up in our slope, right? Because there's a 1/2 on both sides. So what that means is my spring potential energy equation looks like 1/2 kx squared. Now, if that last little bit totally confused you and you have no idea what I did, that's okay, as long as you can remember, or even just use your reference table to figure out that the spring potential energy is 1/2 kx squared. I just wanted to show you guys where that equation came from and how we could have figured it out using information we already know. So remember, K is the spring constant, how stiff the spring is, and X is the change in length from that natural unstretched length. K is measured in newtons per meter, X is measured in meters. Okay. So we can analyze the energy of two kind of spring systems. We can do them horizontally or vertically. So usually horizontally, we're on a nice frictionless surface and we are stretching our spring out to some amplitude. We'll say x equals a, so that's that x max on that. Okay, we'll throw a mass on the end and we'll pull it out to, we'll say x equals a, the amplitude. And then of course it's going to go back and compress the spring to a negative amplitude. At those amplitudes, that's where we're going to have the maximum spring potential energy, because that's where our speed is 0. And then at the x equals 0, where we have no stretch, that's where our potential is 0 and our kinetic energy is maximum. Then again, at that negative amplitude, we have maximum US and a speed of 0. So here we're oscillating between maximum potential and maximum kinetic. Now, if we were between 0 and A, we would have some combination of spring potential and kinetic. But we could say that spring max ends up equaling KE max, so 1/2 kx squared max equals 1/2 mv squared max. Now, one thing to pay attention to is that the mass cannot cancel here like we are used to. So if the mass increases, then our maximum velocity is going to decrease. So if I were to attach a larger block to this spring, if I stretched it to the same amount, this larger mass would mean that V has to decrease because this spring potential energy would be remaining the same. So that's one important thing to pay attention to because we're really used to mass canceling. So now let's talk vertical springs. So we take this and just put it vertically, and I'm pretty sure I show us a nice vertical spring. Yep. So there's a vertical spring. It just bobs up and down. Whee! Bum, 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 bum. Bobbing up and down. Now, we'll look more into the oscillation aspect of things when we get to simple harmonic motion. But that initial no mass attached, that's our natural length. That's our x equals 0. And then we might add a mass on top of it or mass onto it, causing it to stretch to its equilibrium point where our net force is 0. A lot of words, I know, I kind of mean similar things. All right, but that equilibrium length, that's where our net force is 0. And then maybe we stretch it even further to make it oscillate back and forth. And so let's say we initially, once we add the mass, get stretched a distance d, and then I stretch it a distance a to make it bob up and down. And I'm going to say that my stretch a is greater than the stretch from equilibrium. So what that means is when I bob back up, I end up above my natural length. And we're going to say that this is a spring earth object system, so I can have spring potential and gravitational potential and kinetic. Okay. So, so there's my, right, the upper A and then the lower A. That's where my speeds are 0 because I'm changing direction. So those are where my kinetic energies are 0, kinetic energies are 0. So since that upper A is the tallest point, that's where I'm going to have maximum UG. Since I'm my highest height, my kinetic energy max is at that equilibrium position as I'm passing through that position, kind of the middle point. And then where my spring is stretched the largest, right at the bottom, that's where I have maximum spring potential. Okay? At that equilibrium position, I do have all three kinds of energy because I am stretched from my natural length, I am at a height, and I am moving. Okay? That just happens to be where the kinetic energy is at a maximum. So at that lowest point, that's where I have no speed, no height, so I have only spring potential. And then at the top with UG max, I do have spring potential because I am compressed a little bit from my natural length. So I do have some US and UG at the upper location, right, where my speed is 0. So I'm kind of oscillating between a combination of UG, KE, and US. And it's definitely a weird problem, but like I said, we'll talk more about it when we get to spring or simple harmonic motion. And again, remember that the mass does matter here. Mass is going to impact maximum speed and height and things like that because it's not going to be able to cancel. Okay. Now, our spring potential energy is going to equal 0 when we are passing through that natural length. So that's where I'll have UG and K. So once I'm passing through that natural length, right, which corresponds to this point here, that's where my spring potential is 0 because that X is change in length from natural length or rest position. Now, a lot of the times in this unit, we'll be dealing with horizontal springs, But I just wanted to go through vertical springs with you in case it does come up in a question that we are working on. But we will address that more when we get to simple harmonic motion. For now, definitely focus on the horizontal springs, where we're converting spring potential to kinetic. Of course, keeping in mind that mass cannot cancel, so mass will impact the speed, which we are very used to mass canceling. It does not cancel here, so make sure you pay attention to it. Right, and I think that is the end. All right, second time, hopefully better. Who knows? Have a good day.